We will continue with vector operations, and we were discussing vector multiplication, and vector multiplication is not simple. It can have three different type of multiplication. And the first type of multiplication is multiplication by scalar. So we have a vector A and we have some scalar number alpha, and we can form another vector which will be simply alpha time A. So we are just multiplying a scalar number to a vector. So this is the simplest one, and it's also distributed. If we have something A plus B is equal to alpha A plus alpha B. So this is simple multiplication by a scalar. So two other type of multiplication are, the first one is the dot product or scalar product. So if we have a two vector, again A and B, the dot product is defined as A dot B is equal to AB cosine of theta, where theta is angle between these two vectors. If we have a vector A and we have a vector B, so this is angle theta. And geometrically, or the physical meaning of this dot product is, if we have these two vectors, so the dot product is in fact projection of vector B on vector. We have vector A, we have vector B, so we have to draw a projection. So the projection is this length, and this is projection of vector B over A. So this length is in fact AB sine of theta. So A dot B is equal to AB cosine of theta. Projection of vector A on, or vector B on vector A. If we draw the projection of vector A to B, then the projection will remain the same. So if we have projection of B A over B will be dA cosine theta, and in fact these are scalar multiplication. We can change the order, so B dot A is equal to A dot B. So scalar or dot product is commutative. Also, the dot product is distributive. If we have three vector A, B, C, and we are taking dot of A with B plus C, then it will turn out A dot B plus A dot C. So the dot product is commutative. The projection of two parallel vectors vector is A, one is B. So projection A dot B is equal to A B. So for a parallel case, we have theta is equal to 0 and cosine of 0 is 1. And for self projection or dot product of a vector within it itself will become A dot A is equal to A square. And for two perpendicular vectors, if we have two perpendicular vectors, so say this is vector A, again this is vector B, A, B. If we take the projection of A on B or B on A, the projection is 0. So for two perpendicular vectors, A dot B is equal to 0 and theta is equal to 90 degree, and we know cosine of 90 is 0. So here is an example. We are asked to find the example is 1.1 in Griffith book 1.1. So we are given C is equal to A minus B, and we are asked to find self dot product. We have to find C dot C. So C dot C will become C square is equal to A minus B dotted with A minus B. So the right side is C, the left side is C square. So the right side will become A dot A minus A dot B minus B dot A plus B dot B. So it turned out to be A square plus B square minus 2AB. As the dot product is commutative, we can take B dot A to A dot B and then we can add them. And it will turn out A square plus B square minus 2 A B cosine of theta c square is equal to, and this is the law of cosines. So c square, that is the difference of vector A and B, is came out as law of, it can be expressed as a vector self dot product in terms of law of cosines. So next is cross product. So cross product is cross product or vector product. Dot product is a scalar product, but cross product is a vector product. So the cross product is defined as, we have two vector A, and then the cross product is A B sine theta with n unit vector. So n is unit vector, which is, we already said, is magnitude is 1, and the direction of this n unit vector is perpendicular to the plane of A and B. So if we have a plane, like we have two vectors, so we have vector A, vector B, so they form a plane, and the normal to that plane is normal, which is the direction of the cross product. So we have, the problem is we have two normal direction. One is upward and other is downward. To remove the ambiguity, we used to use right hand rule. For right hand rule, we put our fingers in the direction of the first vector. Say we pointed the fingers in this direction, and then we bend them to the other the vector B, towards the vector B. Then our thumb will point the direction of the normal. So in this case, if I put my fingers in the direction of A and curl my finger to B, then direction is outward normal. And if I take from B to A, which will be not A cross B, it will be B cross A. So my fingers curl towards the vector A, and then my thumb is pointing downward. So in that case, the direction of the normal is downward. And we can see from this that A cross B is not equal to B cross A. So it's not commutative. In fact, its direction is changed. So in fact, A cross B is minus B cross A. It's a change of direction of the vector. So you can put a negative sign to the normal, and you will come up with the same thing. The cross product is also distributive. So if you have a cross A cross B plus C, then you can put A cross B plus A cross C. And geometrically, what the cross product tell us? So we have two vectors, vector A, vector B. Geometrically, the cross product A cross B, the magnitude, tell us the area of the parallelogram, which is the area of this region. So this whole region area is area of the parallelogram generated by vector A and B. And sine of the angle AB, sine of theta, and normal. So if two vectors are parallel, means if theta is equal to 0, then A cross B is equal to 0. This implies that the self cross product A cross A is equal to 0. So we will continue with the next section in next lecture. See you in next lecture. Bye.